My thesis is about creating an architecture for opportunistic collaboration as well as an implementation for that. So let me start off by describing what I mean by that. I'm sure opportunistic collaboration is maybe not a definition you're familiar with, and I intend it differently than it's used elsewhere as well. So in general, in a programming environment, when we talk about collaboration, what we mean is the work coupling between two actors. So that is, we assume they're working on the same artifact in the same view, so the same section of code. That's traditionally what collaboration means. So for example, the first collaboration systems were what you see is what I see systems, which is where both programmers literally have the same view, and changes from one programmer show up for another. That's a pretty tight form of work coupling. It's since been made looser, and I intend it to be loose in this presentation as well. So work coupling for me is just anytime one actor is aware of the activity of another, and that somehow influences their work. As for opportunistic collaboration, it's collaboration, but with the key distinction that it's unplanned collaboration. So it's not two people getting together beforehand and saying, we're going to work on this problem together. It's each one is working individually on their own task. There's some event triggered by one of them, and this initiates collaboration between the two of them. So this is nice because it allows for mixed focus collaboration, which is where one party is working on an unrelated task. The other party, something like this happens that says, listen, you have a code conflict. You're both editing similar portions of the code. You need to come together. They can collaborate and then go back to working on separate things. So this is a way to get looser collaboration than that what you see is what I see collaboration. And it's directly related to the problem I'm interested in solving. So the driving problem for this thesis is we wanted to build a tool to help in the instruction of programming courses. We want students to be working in Eclipse. In this example, we specifically have Eclipse in mind, but I'll talk about how to generalize that later. There's some sensor that records the state of Eclipse. That's things like what's in the editor, what's in the console, and sensors which record the state of the student. That's how much frustration they're feeling, how much difficulty they're experiencing. And that information gets passed along to an observer who, in the example we had in mind, is an instructor, but again, I'll loosen that up later. And then based on the information they're receiving, they can choose to opportunistically collaborate with the student or not. So if the student is in difficulty and the instructor decides they can help them, we want to provide some way that they can join the student's loop here and help them solve their problem. Of course, it doesn't matter if it's Eclipse or not. The same workflow applies for any programming environment. So for example, IDE1, which is an online browser, it's the same workflow. So whatever implementation I come up with to support this Eclipse scenario, ideally it should also work in any environment. There's no reason for the implementation to be bound to Eclipse because people use many different environments. Similarly, this workflow, it generalizes to different environments, but this workflow is actually more general than just programming even. For example, here's a non-programming application of this workflow, fitness trackers. So instead of having a student programming, you have a walker who's trying to live a more active lifestyle. And their fitness tracker, like the sensor, records their activity. It gets pushed through an anomaly detector. So if the walker is taking less steps than usual, that triggers an event. The walker's family, friends, coach, etc. This is like the instructor in the programming example. They can then join the walker's loop, and the collaboration they do is offer encouragement to get that person back to their normal levels of activity. So this is an example of the loose way we mean collaboration. This workflow is actually even more general than this. The actors, oh, okay, I'll talk about that in a second. I want to talk about this too. So that workflow brings up something interesting that we didn't talk about in the programming example. In the fitness tracker example, you have the static actors, people like this walker. In their loop, they're actors. In other people's loops, they can be observers. So you have a connection of all these people's different loops. So I may be walking, my friends may be walking. We can be aware of each other's activity. And that's a type of collaboration. I'm aware of what someone else is doing, and because of it, it affects what I'm doing. If I see my friends doing a lot of activity, I'm going to be encouraged to do a lot of activity myself. And so this idea could be applied back to the programming example. perhaps if students are aware of what their peers are doing, that can influence their behavior, and it may encourage them to work more on assignments or begin assignments early. So this idea of networking loops together and having actors in one loop be observers in other loops is a nice idea that comes about from this example. So as I was saying before, this is even a more general version of this kind of workflow. Here, the actor is a machine rather than a human. So this is a workflow that demonstrates a project that's going on at UNC right now. It's supposed to be a way to detect when these HVAC units begin to fail, to catch them before they actually do fail. So we have the same kind of flow. The HVAC unit is affecting some environment, in this case a room, through applying heating and cooling. There are sensors which detect the state of the room as well as the actor itself. And so the HVAC unit gets feedback from this loop in the form of, is the room too hot or too cold? If it's too hot, it'll cool it. If it's too cool, it heats it back up. And a human observer gets notified if the anomaly detector detects there's some fault in the system. That could be if it's particularly loud or if the sound is irregular. And then they can collaborate with the unit by inspecting it and then repairing it if it needs repairing. So my point is that these kind of flows are really quite general, beyond just the driving problem of doing programming collaboration between students and an instructor. And whatever solution I come up with should ideally work to some extent with these other applications. So I got 3 goals for the implementation I come up with. Proportional reuse is the one I was just talking about. If they're related scenarios that are similar to the problem I'm trying to solve, my solution should be applicable to those scenarios to the extent that they're actually similar. So Eclipse programming and IDE1 programming, basically the same problem. We should be able to use any kind of difficulty detection that Eclipse is using in IDE1. For more remotely related problems, for example, the fitness tracker, it's still an example of opportunistic collaboration. So it should be able to reuse the opportunistic collaboration tools that our programming scenario uses for this different application. And similarly, the more removed you get, the fewer components you're going to be able to reuse, but you should still be able to reuse the components that are shared between them.
Ask questions now.
Sure.
Go for it.
Can you go back to this slide?
Yeah.
Why is collaboration a subset of opportunistic collaboration?
Any opportunistic collaboration scenario is going to have to support collaboration because you have some trigger, and then based on that trigger, you begin collaboration with someone. So it's not a subset relationship. So, right. So this is a.
This is a Venn diagram.
Sure. Yeah, I understand how that could be confusing. So yeah, you're right. Opportunistic collaboration is a subset of collaboration. So kind of the inverse of the point I was just making. In the same way that other systems should be able to reuse our system, collaboration tools have been widely implemented. We should use those to do the collaboration aspects of our system. There's no need to reinvent the wheel. These systems are tested and they're robust. And if someone's already done something like instant messaging, which people have, we should reuse that if we want to do that in our scenario. It solves tough problems, one of them being scalability. We ultimately want the system to be scalable to the point where anyone on the internet can help anyone else on the internet. So say we have some instructor in North Carolina, they should be able to help some student in Texas. There's been demonstrations that this works. There's internet communities like Stack Overflow, where you do have an internet scale of people all collaborating with each other to enormous success. So our system should be scalable to achieve these same things. Of course, that has as a sub-goal that the system has to be robust enough to support these internet scale loads, and that's why it's so important to do interoperation with existing technologies. So I made the point that all these workflows are kind of the same thing. So before we actually get into designing an architecture, it's helpful to be more precise about how they are all the same kind of workflow. And the abstraction for this that I chose was created by Professor Dewan last year. It's called dynamic hybrid loops, and it's kind of a modification to this classic idea of closed loop systems, which have been around in engineering for a long time. So a closed loop system is just where you have some machine which is modifying an environment. You have sensors inside that environment that give feedback to the machine, and based on that feedback, the actor changes its behavior. So an example could be a controllable oven. You type in a temperature of the oven, it has some heating unit that heats it up, some thermometer. If the oven is too cold, the heating unit continues to heat. If it gets too hot, the heating unit shuts off. So the modifications this makes is it's dynamic in the sense that it has the notion of potential actors. So the stack actor in the example I just gave is this heating unit. Dynamic hybrid loops have actors which can choose to join the loop based on information received from the anomaly detector. So an example would be like a sprinkler system. And if the oven gets too hot, the sprinklers can decide to join this loop, come in, turn on, and cool the system down. These loops are hybrid in the sense that the actors can be machines or humans. So classically, in engineering, these actors are always machines. It's always something like a heating unit or a motor. In the programming example, clearly, both of these actors are humans. One is the student, one is the instructor. In the example I gave with the HVAC unit, you have a mix between humans and machines. So that's why these are called dynamic hybrid loops. Now, people have already implemented similar systems that solve this driving problem. The one most closely related to my work is called Eclipse Helper. It solves exactly my driving problem. It is a way for instructors to help students out in programming classes. The big way it does this is by doing automatic difficulty prediction. So it has this difficulty predictor module here. It collects information about the student's programming activity, such as how many inserts they're making into a document, how many deletes they're doing, how much scrolling around they're doing. And based on that, it computes if the student is experiencing difficulty or not. And it pushes that information to some server along with, it collects the student's workspace. So when a student's in difficulty, the observer, the instructor is notified. They can then view the workspace, try to figure out what's going on. If they determine there's a problem, they can communicate a solution to the student via email. So of course, if this solution met all my goals, there would be no point to my thesis. So it turns out that it doesn't really meet many of the goals that I'd set out. It has barely any proportional reuse. It was designed specifically for Eclipse. It was not designed with supporting these other scenarios. So it's very tightly coupled to Eclipse. It wasn't designed with scalability in mind, designed to be used in a single classroom by a few instructors. And interoperability, the only thing it works with aside from the email client is this tool called Fluorite, which captures low-level Eclipse events. So it depends on that to catch those events, and then it uses those to make its difficulty prediction. So Eclipse Helper solves the driving problem, but doesn't do it in the way I want to do it. It doesn't satisfy these goals. But it is a working solution. So rather than beginning from scratch, I start with Eclipse Helper, make minor modifications to it to bring it closer to my goal system. So I'm going to take you through a series of small changes to Eclipse Helper to bring it such that it satisfies the goals I had in mind. So the first thing we're going to deal with is the sensors. So in Eclipse Helper, I mentioned there's this difficulty predictor module. This is really performing two logically separate tasks. It's an event sensor. I said that gets passed off to Fluorite, but it has an event sensor in here that's capturing events from Eclipse. And then it passes those into this difficulty predictor tool, which ultimately makes the predictions. The thing to notice here is that this difficulty predictor isn't performing anything Eclipse specific. The logic inside of it has nothing to do with the fact that it resides inside of Eclipse. The same difficulty predictor should be usable in any programming environment. So the idea here is to break out anything that's not environment specific onto the server side. That way you don't have to duplicate logic between plugins, between different environments. So for example, if this were to reside in Eclipse, if you were to implement the same system in the browser, you'd have to duplicate this logic, which is unnecessary because it's the same logic. A benefit of doing that is that your sensors now send lower level events. So now the events you're sending to the server are environment specific. Of course, you want to morph them to be more abstract events. So in sending Eclipse version of an insert event, you want to convert that into some virtual event so that the single difficulty predictor can handle events from both the browser and from Eclipse. But the events you're sending are like things like student performed an insert, student performed a delete, rather than student is in difficulty. And the advantage of doing this is that the data from these sensors can be used in ways that you didn't originally intend for it to be used. So while you may have set up the event sensors to be used strictly for difficulty prediction, someone can come along and add a feature so that those events can be used for something else, such as tracking programming activity. You could use time to track programming activity, but if someone types twice as fast as someone else and works for half the time, they could be argued to have done the same amount of work, even though they did not spend as much time. So to support that scenario of using the events from sensors in different ways than originally intended, the server side has to be extensible. In Eclipse Helper, everything in the server is hard-coded into the server. It all runs as a single process. And that means if you want to add extra functionality to the server, you have to modify the source code or come up with some other clever hack. I argue that the server side should be easily extensible and have a way for users to add additional functionality to the server. So the server shouldn't have any of this stuff hard-coded into it. These should exist as external processes that the server interacts with. So that allows, for example, this example of the event recorder. So you may have originally intended for these events just to be used in difficulty prediction, but someone may decide they want to use those events to record some metric of programming activity. And by having the server be extensible, you can now do that. It also allows your server to support new sensors. So when you may have thought your server was just handling events from programming activities, someone may come along and realize they want to also do difficulty prediction for writing activities, and that's going to require a separate difficulty predictor because those are fundamentally different tasks. So you'll have to add another component to your server to handle that. That's why you see Google Docs over there. The events coming from here go to the writing difficulty predictor rather than the programming difficulty predictor. So clearly we're going to need some design pattern that allows for message routing because the server is passing these messages from the event sensors to these other components, but it's doing it based on the content of the messages. The writing difficulty predictor isn't receiving messages from Eclipse. So there's already a design pattern that achieves this. It's called the message bus. So message bus is just a way for applications to communicate with each other, separate applications. So we're actually doing something a little more specific. It's called message bus with content-based publish subscribe, which means that each one of these message bus clients tells the message bus the types of events they're interested in hearing about. And when the message bus receives those types of messages, they get forwarded. Otherwise, they don't get forwarded. So when the clients are initially started up, they tell the message bus what they're interested in receiving here in the form of regular expressions, but it could be any other way. Then when a message comes in, the message bus will forward it to the appropriate clients based on what messages they said they were interested in receiving. One important functionality of the message bus is that it doesn't only pass messages from the sensors, it can pass messages between applications. So the difficulty predictor can pass messages to the notifier, which is just some generic client that makes information public to instructors and other students. So there may be a delete event that comes in the message bus. The difficulty predictor decides a student is in difficulty. Instead of publishing that itself, that's not really difficulty prediction logic. That has to do with how you get information to the outside world. So we don't want to implement that logic inside the difficulty predictor because then any message bus client that needs to communicate information to the outside world is going to have to redo that work. Instead, we should have modular message bus clients that only do one task and pass off other things to other message bus clients. So in this case, the difficulty predictor doesn't know how to publish information, but it can send a message to the message bus, passing off that responsibility to some other client. And I'll get forwarded to the notifier, and the notifier can publish that. So basically, we want modular message bus clients that do one job. All right. Still talking about the sensors. In the same way that we need to have this extensible server, the client side also needs to be extensible. In Eclipse Helper, the difficulty predictor and the workspace share are things that are hard-coded into this main Eclipse plugin. If we want it to be extensible, that can't be the case because we don't want users to have to modify the source code to get the system to meet their own unique needs. So we need to separate out those components. So there should be one main thing that talks to the message bus, and then these other things like message bus clients that talk to that main thing. And those are supposed to be easy to implement so people can tweak the system to meet their own custom needs. All right, so this is going back to the example I showed in the fitness tracker. While we were just talking about how the message bus clients and the plugins inside of the environment itself need to be extensible and people can make their own clients for their own needs, I claim that there are also some universal clients that are useful in any application. For one, they're useful in the 4 motivating examples I gave, but I claim they're also useful in most other applications that have this workflow. So the first one is harkens back to the example in the fitness tracker where we need to notify all members of this loop, all actors and all observers, about the state of other people in the loop. So all information is being sent from these actors to the message bus. We don't want to publish all of it to everyone. For example, you're probably not interested in receiving a notification every time someone makes an insert into their program file. So there has to be some kind of aggregation that's going on, because you may be interested in knowing how many students made inserts in that specific day. So that's what this aggregator is doing here. And it's that client piping that I showed earlier. So the aggregator does something with the event received from all these different actors, condenses it, and then says this needs to be published to all these people. So I claim that this notifier is a universal message bus client. You always need something to get information back out to people in the loop. I want to point out also that what it's doing is it's a form of instantaneous state. It's just publishing one notification. You can see what the state of the system is at that point in time. It has no sense of history, which motivates the second client I claim is universal, which is a cloud store. So this is a file repository with a notion of history. So you're storing files here, but you're also storing the history along with these files. I call it a cloud store because it needs to be scalable since we have a lot of users, and it's ideally accessible from many different devices. This is important because I claim that while this instantaneous state that's provided by the notifier is necessary, it's not sufficient. If you just get a notification that a student is in difficulty, that's not necessarily enough to help resolve their difficulty. You need to look at the state of the programming environment as it is now, but also as it was in the past, to really help them efficiently at least. So you need to have both this instantaneous state and this historical state. And I want to point out too that neither of them is sufficient. So I already made the point that the instantaneous state isn't sufficient, but neither is the historical state. You can't just have this version control system storing everyone's files, because then you'll never recognize who's in difficulty and who needs your help. So you need an instantaneous state to trigger you to look into what the historical state is of a specific person. So these two need to be coupled together. And that's what I'm showing in this example. So say we get some sensor data, goes to the aggregator. The aggregator decides it needs to make a post through the notifier, but needs to be coupled with some historical information. So it requests a link to the historical state of whatever that event is from the cloud store. Cloud store passes it back, and it finally goes to the notifier. So the notifier makes an announcement of whatever event it wants to notify people of with a link to historical information. So these two need to be coupled together. You need instantaneous state, but it needs to also be linked to some type of historical state to really be useful. All right, so when we want to do explicit collaboration, that is, an instructor has decided that they're ready to help a student, in Eclipse Hopper that happens through email, I claim that's a bit of a clunky and outdated solution. For one, it seems a little overkill to send an email if you're just pointing out a syntax error in some student's code. We could use something lighter weight like instant messaging. It happens outside of the programming environment, so a student has to leave Eclipse to go check their email. By the time they check their email, the help that they received may no longer be applicable. They may have already solved their problem. And then it has no artifact attached to it. So there's been a lot of research into how people communicate to each other, specifically when they're talking about code. And having something to point to dramatically reduces how cumbersome a conversation is. If you can say, I'm talking about this section in the code, rather than having to describe what you're talking about in words. So having the actual editor contents shared between users is critically important. So we need shared editing to have a really efficient system. But I also claim it needs to go slightly beyond shared editing, because we don't want the student to have to mess around with figuring out how to set up a shared editing session. That could waste a lot of time. It would be ideal if the instructor can just click a button and immediately begin a shared editing session with the student. So I call this concept receiver-initiated shared editing. And this is something that doesn't exist in almost any implementation of shared editing for privacy reasons. So any implementation we do will have to kind of tweak an existing system to achieve that. So that completes the transformation of Eclipse Helper into my goal system. A recap of what we've done is we've broken out any non-environment specific processing from the client side onto the server side. We've made the server side extensible so you can add new message bus clients. We've done the same thing on the client side. You can add new sensors to collect different information. I've picked out these two universal clients, the notifier and the cloud store, and claim that they're useful in all these different applications. And then just improving the communication tools to make this explicit collaboration more effective. So this is the complete architecture. Sure. Yeah, let me know if you have any questions about this slide or how these pieces fit together. So the architecture hasn't done anything for our goals of scalability and interoperability. Those are questions that are resolved by the implementation. The architecture has set up a system that is ideal for proportional reuse, though, through the points I just made, that we have extensible servers and clients, and that clients are just collecting environment-specific information. So the implementation will address these two remaining issues. So the first one to deal with is how do we implement these sensors such that they are extensible, such that people can write specific sensors for their specific applications. And for the remainder of the implementation, I'm talking about implementing this in Eclipse specifically. So Eclipse has a really nice framework for this because it was designed to be an extensible system. Their plugin composition framework kind of achieves this already. So there's some master plugin that has a way to communicate with the message bus. It exposes an extension point, which is this Eclipse concept of how different plugins interface with each other. So if you want to write a sensor for this, you simply target the extension point that it created, which will throw you into an extension registry. And then when this plugin is started up, it can query the registry, find out other plugins that are targeting it. It will start them up. And then anytime they want to send a message to the message bus, they can just call this publicly exposed method that it sets up. So this is actually a really nice solution. If Eclipse didn't provide this for us, we would have to do something similar to a message bus to achieve this kind of easy extensibility.
What kind of new sensors do you imagine being added to Eclipse?
So one would be, there's not necessarily new sensors, but sensors that already exist being used as part of the system. So there's a sensor in the department right now called the grader. It does automatic grading of assignments. That would be really beneficial to interoperate with this. So you can say this student is in difficulty, but let's look at their historical grades. They usually make A's on assignments. So they may figure out this problem on their own. It's also helpful, that plugin specifically for this actor-to-actor communication. So everyone in a classroom can be aware of the grade distribution of everyone else in the classroom automatically. So that saves instructors a lot of time from having to manually publish that information. So that's
also, if you're repeatedly editing without changing your grade, that means you're not making much progress.
Sure. Yeah, so that's one plugin that we've talked about a lot that would be really useful to hook into this. I'm going to talk about some others that I have implemented right now. So this one is pretty useful. Editor contents collector that grabs the contents in the editor, pushes those to the message bus. Console contents collector does the same thing, but with a console. So anytime you run a program, it'll grab the output. But maybe more importantly, anytime you try to compile a program and you get compiler errors, those also get output. It has a time tracker built in. So anytime you begin editing, it says you began a new session. Anytime you go a certain period of time, such as 5 minutes without editing, it says your editing session ended at your last edit. And it'll send that session to the message bus with the start time and end time. And it has a self-reported difficulty sensor, which it just provides a UI to the student. They can select on a scale of 1 to 5 how much difficulty they're experiencing. It gives them a little form they can fill out saying what they're having trouble with, and they can explicitly request help. So these are 4 sensors I've implemented. Why is the time tracker interesting? So that's mostly for this actor-to-actor communication collaboration, so students to students. So the instructor isn't involved in this part of collaboration. In the same way that in fitness tracking, it's helpful to know the activity of your friends, it's also useful to know how much time your classmates are spending on assignments. It could encourage you to spend more time on assignments if you're below the mean, or if you see that assignment is taking students a lot of time, you may be prompted to start the assignment earlier. So it's useful for that, and then instructors can actually gauge how much effort students are putting into the course. So if an assignment is a 20-hour assignment and an instructor intended it to be a 15-hour assignment, they can tweak the assignment in future years. So it's an objective feedback mechanism. You don't have to, listen to students complain and then kind of account for how much they would complain about a moderate assignment. Okay, so the message bus implementation. Many message bus implementations exist. For example, .NET has its own message bus implementation. GitHub has about 10 message bus implementations. I didn't use any of those because they're all heavy duty. And by that, I mean they support a lot of functionality that I don't need. And interfacing with them is difficult, and sometimes it requires that your clients are written in a specific language themselves. And I wanted people to be able to write clients in any language whatsoever. I also wanted the message bus to be able to start the message bus clients, because you could have a large number of message bus clients, and manually going in and starting all of your message bus clients could be quite tedious. So I need a message bus that has this additional functionality of being able to start up clients as well. So I wrote my own message bus, and it does all of its message passing through standard in and standard out, which means you can write these clients in any language, and it's easy to write them. You don't have to deal with complex things like sockets, which I'm sure some people would be scared of writing a message bus client that had to work with sockets. So what happens is there's some list of clients, and anytime you have a new client, you have to append an entry to this list. That's what this thing on the far right is. And each entry in the list has a command that would start that client. So the message bus, when it starts up, goes through this list and actually executes those commands and creates a new process for each one of the clients. And then it grabs a handle to its standard input and standard output, starts up a thread that just continuously listens to the standard output. When it wants to forward a message to a client, it writes to its standard input. As you can see here, here's an example. This is just the protocol I came up with to handle this message passing. Not terribly important. The important thing is that this is all done through standard input and standard output.
Where do I identify when I want to get messages about it?
Where do you identify what? Oh, so that's what these red arrows are. So when the clients are started up, they send a message to the message bus containing a regular expression that lists the type of messages they're interested in receiving. And every message has this tags field, which is just an array of strings. The message bus will check these regular expressions against each entry here. And if it matches, it'll forward it to the client. So I wrote libraries for 3 popular languages, Java, Node, and Python, to handle all this protocol-y stuff, because it may be difficult to remember that the first thing you write when you want to send a message is the number of characters in your message. So I took care of all that logic, as well as setting up kind of this thread that always listens to your standard input to see if the server is trying to send you a message. So for example, here's what it looks like to write a client in something like Node. You just create this object, and it has exposed methods like send tags. This is how you say what messages you're interested in receiving. Set input finish callback. This is a function to call whenever you actually receive a message, and the argument to that function will be the string of the message. And then this output is how you actually output to the message bus console if you want to notify someone listening to that. So it's pretty easy to write clients if you take advantage of these libraries. It's even easy if you don't take advantage of those libraries. So you can write clients in any language that has standard in, standard out, which is, as far as I know, every language. All right, so now we have to implement this communication between instructor and student. It needs to support instant messaging within the Eclipse environment itself, and it needs to support this receiver-initiated shared editing. So there's a tool that does this. It's called ECF, which is the Eclipse Communication Framework. It has a nice UI for instant messaging and shared editing as well. It builds on top of other communication protocols. One of those is XMPP, the Extensible Message Passing Protocol, which just uses XML. It's a lightweight protocol. They claim to have libraries for every language, as well as software for every platform. Software meaning both servers that implement this protocol, as well as things like chat clients. So I went with that because it's widely accepted, open source, lots of implementations, proven to be robust and scalable. So it's how communication works, is we run one of these XMPP servers. OpenFire is one of the leading open source implementations. Set up a modified version of ECF. I say modified because I had to tweak it to support this receiver-initiated shared editing, because off the shelf it just does vanilla shared editing where the person doing the sharing initiates the session. Inside this, we're using XMPP. And then on the instructor side, if they're just doing instant messaging, they can use any number of existing clients that are out there. One is called a Spark, which is instant messaging. There's desktop ones, there's mobile ones, so the instructor could do instant messaging through their phone if they wanted to do on-the-go help. Or if they want to do shared editing, they can be in Eclipse and be using ECF themselves.
So did you change the source code of ECF, or did you use Reflection? I forget.
So I didn't change the source code. So ECF is an Eclipse plugin. It has exposed a couple methods. So I wrote my own plugin, and I have a special version of that shared editing object that just extends the vanilla one. And it's what it does is when it receives a specific type of message from the instructor, so the instructor just ends up typing a message that says share to the student. When it receives that message, it automatically goes in there and starts off a shared editing session as if the student went in and went through the manual process. And I'll show an example of that later. All right, so that's how two humans communicate with each other. I haven't talked about how messages get from the sensor to the message bus, because presumably the message bus lives on some server machine. It doesn't live on the student's machine. So we have to send that information. Again, that also has to be a scalable, robust solution, because we intend to have many students connected to the server, so it has to be able to handle a lot of connections. Fortunately, it turns out that we can reuse our communications for human-to-human communication server for this type of communication, because XMPP is a pretty flexible protocol. So we just set up a connection within the master plugin. Again, this is why it's useful that XMPP has libraries for every language. They have a library for Java called SMAC, so it's pretty easy to set up one of these connections and send messages through the server to another connection that we set up on the message bus. Again, the message bus is written in Java, so it can just use that SMAC implementation. But you can write XMPP clients in almost any language. For example, I've written one in JavaScript to support that browser scenario, and I'll talk about that later. So we only have to run a single server to handle communications for both human-to-human communications and this master-to-message bus communication.
So you could have used sockets also, right?
Could have used sockets as well. Again, the idea here is we're trying to achieve the interoperability goal. If we were to use sockets ourselves, we're writing our own server that has to be robust and scalable, and that's a tricky problem to solve. XMPP, specifically OpenFire, has already solved that problem, so we should just use their implementation.
You could have used sockets to directly send message to a message. I mean, directly.
Sure, but then if we have 2,000 students, that's 2,000 socket connections on the message bus.
And also authentication, right?
Right, so there's a privacy concern here. So the events that we're sending we're talking about the contents of a student's editor, their grade information, how much time they spend programming. That could be considered pretty sensitive information. XMPP is a proven secure protocol, so we don't have to worry about doing all these security checks, which again is a difficult problem to solve. So we should use our goal of interoperability and work with some existing system that has already solved these problems.
And also, you know who the information belongs to.
Sure.
So it has a notion of users.
Yes. Yeah. So I should add that. So there's an account associated with all these XMPP connections. So we can tie back this information to a specific student, which is helpful for putting their files in a file store. You need to tie a file to a student. Just having a bunch of files and not knowing who they came from is not very useful. So yeah, it automatically takes care of the idea of users and accounts, which is good because then you can, it's more security. You can't just have strangers using your system. They have to have an account on this XMPP server, which you control. All right, so how do we implement this cloud source? As I said, this is a file repository with a notion of history, and ideally it's a scalable solution so that we can have a lot of files on there from a lot of different students, and it's accessible from a lot of different devices. So Google Drive actually turns out to be an ideal tool to interoperate with to achieve this. Google Docs already have a notion of history attached to them. When you make a change to a Google Doc, it automatically stores a history revision edit there, and you can go back and view the history of any Google Doc. There's also third-party tools that do that in more fancy ways, and I'll show an example of that later. So basically, we set up a folder in someone's Google Drive which contains all information from a specific class. Each student in the class gets their own folder, and then information from their editor gets pushed to a corresponding file on the Google Drive. So anytime they make a change to their file, that change is mirrored on the Google Drive itself. So you automatically build up a history of this file. It's accessible from mobile devices, from any computer, it's scalable, and it has security.
So each message bus server is associated with one Google Drive account name?
No. Oh, yes, that's right, sorry. So when you first run this CloudStor client, which is a message bus client, it goes through and asks you to authenticate your Google account. You can pick which Google account you use. If you ever want to change the Google account that's being used here, you can go ahead and delete the file that's storing that information. So the idea is that whoever instructor is running the class sets up some Google account to store information from that class.
So presumably I could have multiple instructors tell the Google, your message bus that, I listen to messages of this kind, students of this kind, and then your programming environments and students can go and say which instructor they're mapped to.
Oh, sure.
So that different students, or you could have a separate message bus client, I suppose.
Right.
Message bus server, I suppose. But presumably you can do this routing also, students to instructor also.
Right. Sorry. All right, so that's one of the universal clients. The remaining one is this notifier. So this needs to be able to disseminate information to all actors, all observers in the system. So again, it needs scalability, and it's just a tool to display instantaneous state. So for a lot of the same reasons why Google Docs is a good tool to interoperate with, Facebook is a good tool to interoperate with here. It's proven to be scalable. It has a familiar UI. It has a easy to use public API. So what happens is the notifier client just makes API calls to Facebook. So it can publish either text statuses or photos. And again, we also have a notion of security here. An instructor can have a course Facebook page and set up who gets to view information on that page. So this is, again, achieves scalability and solves some security concerns. And it's accessible from mobile devices, from any desktop, and a familiar UI. So we're done with implementation. This is what the server side looks like. This should remain the same between any environment, and ideally between different applications as well, which means this doesn't have to be re-implemented. This can be shared between all the scenarios I talked about earlier. This one's a little simpler than the architecture slide. Then this Eclipse stuff. The goal is that anything that gets implemented in Eclipse should be stuff that is specific to Eclipse, because we don't want to, again, duplicate logic between, for example, online IDEs. So what it does, it has a CCF connection, which has an embedded XMPP connection. These two are separate connections, I want to point out. This one handles the actual human-to-human talk. This one handles forwarding messages to the message bus. They could be the same, but then that gets confusing, because if message bus clients ever want to talk back to one of these plugins, what happens? Does it go to this one, or does it show up as a chat message from the message bus? So it's important that these are actually separate connections. And then all these are just the plugins I wrote. People can come in and write their own, and they just interface with that master plugin. And when they want to send a message, they call its expose send message method. So I also implemented this, as I mentioned, a really rough version in Chrome. It does a very simplified version of what the Eclipse one does. It has a chat client, which I just interoperate with another JavaScript tool for doing XMPP chat. It scrubs the DOM of several online IDEs and grabs editor contents and just writes those to the message bus in the same way that the editor contents listener in Eclipse does. This was just meant to demonstrate that the server side remains exactly the same. You don't have to duplicate any of that code to support a browser like this. And something like collecting editor contents, that's something that necessarily has to be reproduced in every environment, because there's no general way to collect those events unless you have some keylogger on your computer as a whole. And that's a problematic solution for various reasons. In addition, I did this microprocessor implementation to demonstrate how you could use this framework to do things with IoT. So all the one I implemented does is it has a button attached to it and an LED. When you press the button, it appends to a Google Doc the time and the date. So you can see when the button was pressed. That kind of simulates some sensors gathering information from the environment, and the LED will flash when you send a specific message to its XMPP connection. So that simulates how you can affect the environment remotely. And I'll show a video of how that works now. So I have a video demo of all this just to kind of solidify some of the concepts.
Hermes is an Eclipse plugin for students in computer science
Let me know if
courses.
the audio is good.
It does many things and can be extended to do many more, but its two main goals are to allow instructors to provide remote help to struggling students efficiently and to increase students' engagement and success with the course by providing them with metrics about their programming activity and how it relates to their peers. Hermes essentially collects information from a student's programming environment and sends it to a server for processing. The server condenses this information and leverages services such as Facebook and Google Docs to present it in a useful way to both instructors and students themselves. Let's look at several things Hermes currently does. It provides a simple UI where students can self-report the difficulty they are experiencing, as well as explicitly request help. Additionally, the Hermes server has an extension which allows it to publish to a course Facebook page. When a student requests help, a message is posted on the page's wall, which is visible only to instructors, with the student's information and help request. By looking at the page's feed, an instructor can quickly see who needs help and proceed to gather information to help them. The ability to post to Facebook also allows for useful information to be displayed to students. By aggregating the reported degree of difficulty students face, difficulty versus time graphs can be constructed for the current assignment, and students can see how much trouble their peers are having. If an assignment looks to be hard, students may be motivated to begin early. Also, the simple knowledge of how many of their peers have begun work on an assignment may be enough to prod students to begin earlier, in the same manner that fitness watches have adopted the same concept of a status timeline to encourage healthier lifestyles in their users by showing them the activities of their friends. By interfacing with a popular technology like Facebook, Hermes has the advantage of its information being viewable through a mobile app and providing an already familiar UI to its users. Eventually, we hope to use the self-reported difficulty as a training set for machine learning algorithms, which will do automatic difficulty detection. Hermes collects the text in the code editor and tracks changes to it. The server uses this information to create a Google Doc, which mirrors the file in the student's editor. Both the student and the instructor have access to this file, provided the student allows this. Here we again see the power of leveraging existing technologies. Because it is a popular platform, a number of extensions exist to manipulate Google Docs. By interfacing with it, Hermes gains access to all of the features offered by these extensions, in addition to all the features already built into Google Docs. For example, there's an extension called Draftback, which allows anyone with access to a Google Doc to peruse all historical changes to it. If an instructor wishes to see where a student ran into trouble, they can open the file of interest and look at recent changes to it. As another example, Google Docs provides the ability to add comments to a document which are shared between viewers. At the end of an assignment, an instructor could provide feedback in the form of comments on the Google Docs corresponding to the code the student wrote for the assignment. In addition, Google Docs has a mobile application, so all of this information can be viewed on the go. In addition to capturing text from the code editor, Hermes also collects output from the console. The console contents are appended to a Google Doc unique to each student. Instructors can consult this file to see what types of issues students are facing. Hermes tracks how much time students spend coding and breaks this down into time spent on different assignments and classes. While this capability itself is useful, and hence why plugins exist that serve exclusively this purpose, for example Waka Time, it is especially useful when the information is aggregated across all students in a class and all classes in a department. Students are able to see how much time their classmates have spent on an assignment and compare this to how much time they themselves have spent on it. When deciding which courses to take, students could view objective information about how many hours of coding are involved for the typical student in a given course. This time information can be made even more useful when it is correlated with grading information. students can see how much time is required of them if they expect to make an A versus a B. Since all of this information is contained on the Hermes server, an extension just needs to be written which utilizes it. This is one of the main ideas underlying Hermes: to make the information which is collected from the programming environment flexible and extensible, as well as to make the processing of that information flexible and extensible, and such that the processing of one extension is available to another. Hermes provides a communication system that allows instructors to engage with students directly in Eclipse. Instructors can send instant messages to students for issues that can be resolved easily, and they have the ability to do shared editing for more complicated problems. Let's look at a couple of scenarios that demonstrate the situations in which we imagine Hermes will be useful. Suppose a student is trying to concatenate two strings, but uses the wrong syntax and can't make sense of the compiler message, so decides to request help. An instructor can look at the student's console file and their code and quickly diagnose the problem. A brief message to the student should be enough to resolve their issue. Now imagine a student previously had a functioning sort routine, changed a few lines, and now it no longer works. Frustrated, they request help. An instructor can look at the history of the file, see where things went wrong, begin a shared editing session, and help the student resolve the issue. Let's move from looking at the helping features of Hermes to looking at the information features. Perhaps an instructor is taking the bus into work and wants to see how many students have begun work on the latest assignment. They can open the Facebook app and go to the courses page and see a histogram of the amount of time students have spent on the assignment. Or let's say a student is trying to decide whether to work on an assignment or go to a social event. They can check the course's Facebook page and see how much difficulty their peers are having with the assignment and how much time it takes to complete on average. Hermes, both the Eclipse plugin and the server, were designed to be extensible. The base plugin simply connects to the server and exposes a method that allows extensions to send JSON and to receive JSON from the server. Collecting editor and console contents, time tracking, and measuring difficulty all happen in extensions to the base plugin. These extensions are easy to write and can be written by anyone. So if Hermes is lacking a feature you want, you can add it yourself, and your extension is able to use any of the features which exist on the server. So, for example, your extension could create and manipulate Google Docs without you having to write any code to handle this. The server is similarly designed. The base server simply sets up a connection which handles messages from clients. The rest of the functionality of the server, like interfacing with Google Docs and Facebook, happens through extensions. So if the server is lacking a feature you want, you can add it yourself, and your extension is able to listen to any messages which clients send. So, for example, your extension can receive time tracking messages and make histograms that show what times of day are popular ones for students to be coding. It could then leverage the Facebook extension to post these graphs to the course Facebook page. Hermes was designed in such a way that it is in no way bound to Eclipse. It sends information about the programming environment using the XMPP protocol. So in theory, anywhere where an XMPP connection can be created, an implementation of Hermes can exist. For example, we have implemented an experimental version of Hermes that is a Chrome extension that works with online IDEs. The server side remains exactly the same as for the Eclipse version, because the XMPP messages are exactly the same. Hermes is even more general. It doesn't have to be used as an educational tool. It is a tool for collecting data from many devices and aggregating this data in a useful way, as well as providing a way to communicate with the devices. To demonstrate this generality, we set up a microcontroller to work with Hermes. To show its capability of collecting data from a physical environment, we wired up a button, and to demonstrate its ability to receive information, we wired up an LED. When the button is pressed, it sends a message to the Hermes server. This information can be used to append a line to a Google Doc, using the Google Docs extension we saw earlier. JSON can be sent to the microcontroller from any XMPP instant messaging client to control the LED.
Any questions about that video? Okay, so that concludes that. Now I'm just going to talk about evaluating this and how well this architecture and implementation meet our design goals. So the first and most important one is this proportional reuse notion. So there's kind of two ways to measure this. You can look at how many components of the solution I came up with are reused in different scenarios. So for example, this Chrome extension in yellow up here, that reuses all components that the Eclipse plugin that I developed used. The only thing that it does by itself is environment-specific things. Whereas, for example, the microcontroller wouldn't be able to leverage the difficulty prediction tool that would exist as a message bus client. So in that way, we have achieved proportional reuse, and that these tools can reuse components that are shared between it and the original problem, and not tools that aren't shared between it. Another way to look at this is to look at how much new code you have to write for something compared to the original code base to get it to do what you want to do. And that's why I've included all these code counts here. So this is a little bit of a simplistic measure. So for example, the Chrome extension does a lot less than what the Eclipse plugin does. So comparing lines of code there is maybe not a super useful metric. But you can achieve that kind of functionality that you saw in the video with just a 100-line Chrome extension. Something that microcontroller is only about 20 lines of new code, and those are just specific to actually listening to events from that button and writing events to that LED. So that kind of shows that a lot of the stuff can be reused for seemingly different applications, which means we've achieved our goal of proportional reuse. Scalability. So scalability is built into the architecture, having these kind of networked loops where any actor can serve as an observer in another actor's loop. So architecturally, we've achieved that. And then all the scalability issues in the implementation have been passed off to Facebook, Google, and XMPP, which are proven, robust, scalable solutions. Finally, for interoperability, which I just briefly talked about there, we interoperated with Google, Facebook, these XMPP clients, and Eclipse itself. The only place we didn't interoperate where we could have is with the message bus, and I already motivated why we wrote our own message bus rather than using an existing solution. So there's a lot of things that this architecture and implementation have contributed to the field of collaboration. Two interesting things architecturally wise is recognizing this importance to couple instantaneous as well as historical state. And then this new notion of receiver-initiated sharing, which as far as I know, doesn't exist elsewhere. But I think it's important in other collaboration scenarios. The implementation itself, for one, it works. It solves the driving problem of facilitating collaboration between students and instructors. It's also sufficient enough to get some quantitative data about how reusable the system is and how easy it is to extend. And then the fact that we're able to get by using a single server both for the master to message bus communication and human to human communication is a big save on server resources. The message bus implementation is interesting in itself and how lightweight it is and that it operates using standard I/O instead of fancier communication schemes. Then our use of Facebook and Google are also kind of interesting. Facebook is intended as a human-to-human network, but we threw a machine in the loop to mediate the interaction. So it's really human-to-machine to Facebook-to-human network, which has interesting applications. And in some cases, like that microcontroller example, it's actually being used as a machine-to-human network, which is another interesting application in Facebook. Similarly, Google Drive, the content we're pushing it's machine-generated, and it's pushed by a machine. So I think that's a cool concept that could be used in other places.
I'm going to sneak out because I have a bus in 3 minutes.
Sure.
Otherwise it's another hour.
Thanks for coming.
Okay. Very nice presentation.
So while I achieved all those things, there's still some low-hanging fruit that we can grab. Some of these things is just adding more message bus clients. So while there's sensors that are sending this time checking information and the self-report difficulty, I don't currently have a message bus client that's consuming that information. So that stuff you saw in the video is a bit of Hollywood magic. Those things aren't being pushed yet, but adding a message bus client to do that is fairly straightforward. So that's something that I can do in the near future before I graduate. Then the system needs to be tested for robustness. I've only tested it with a couple of connections to these servers. And in a classroom setting, you have tens of connections to it. So just testing that nothing weird happens when the system is used over a long period of time and there's more connections. And then once it's verified to work under those situations, actually deploying this to test in the classroom, would be really interesting. Of course, there's a lot of stuff we can do with this long term. One is to compare with these other systems, because there are a lot of systems that achieve this. Professor Stotts, you have a system that does something similar to this. Last year, Professor DeWan had another student that created a similar system for helping English teachers with students writing papers. So it'd be interesting to see the effectiveness, not theoretically, but actually in the field of what students prefer in their collaboration tools, and if they prefer some UI like Google Docs and Facebook with which they're familiar, or a UI more targeted to actually facilitating this collaboration. Related to that is just doing a field study to see how effective the system actually is in use. Then some more implementations of it. So implementing a version of this for a writing application would be useful for the same reason that Dory Long's presentation was useful on this type of application. Then building a real suite of tools for microcontrollers. This is a real problem in the IoT industry about how to get sensor information from devices available to the outside world. So just making the tools available for microcontrollers better and more comprehensive, because I think this could be a real huge application of this service. And then using configuration management tools to make server setup easier. So when you set up a server, you have to create this XMPP server. You have to set up a message bus. You have to set up all the message bus clients, create that file. If we could just use configuration management tools so that you just run a single script and all that happens automatically on your server, that would be a real win. And then making working with the server easier by having some web portal to work with it. So if you want to add a message bus client, being able to do that from the web rather than actually having to SSH into your server machine and upload these different message bus clients. Maybe eventually having some kind of online store of all the available message bus clients, kind of open sourcing this and allowing people to publish message bus clients, and you can install those into your server with the click of a button. That's all I've got.